I'm sorry? This discussion is webcast, yeah. Yeah. All right. It's about time. Should we get started? Okay, I think we're live. Um, so, hello everybody, and welcome to the first discussion section for EE 140. My name is David Sobel, as it says right here, and my email address is listed here. It's also on the webpage, so you don't need to write it down, and it's also on the handout that's circulating around. Everyone make sure that you get the handout. A quick note about if you send email to me. I get a lot of email at this email address, and sometimes things filter down to the bottom before I can see it. I've got a filter set up so that if you put EE 140 in the subject line, I will notice it faster. So keep that in mind. The other TA for the class is Saurabh Amami. His email address is listed here, and hopefully all of you have the handout that's been circulating around the class. If you don't, where's the stack of handouts right now? I printed out around 40, and there might actually be more than 40 people in this class. So make a copy from a friend, or we'll try to post it on the web. Most of the information here is duplicate from what's on the web. So just to go over it really quickly, I don't know, can you guys see the actual text on the screen? No? Okay. So I'll go down point by point. My name's David Sobel. My email address is listed here. It's also on the web page. The discussion section is Fridays 11 a.m. to noon now in McLaughlin 203. It is webcast, and you can get these sections on the website webcast.berkeley.edu, the same place as the lectures. I don't know if they're broadcast live, but you can get them whenever you need them, and obviously they're backed up, so you can view them after the fact. My office hours are Fridays 9 a.m. to 11 a.m., 2 hours basically right before this section in Corey Hall, Corey 297. All of you should know what the web page is for the class by now. And if you don't have an instructional Unix account set up yet, do it. You'll need it for the first homework set in order to run Spice. The instructions for setting up a new account are on this sheet, and for those of you who don't have this sheet, the information is also on the web page. The next point down here is about card key access. This is also information duplicated from the web page. Oh, great, it's zoomed in. So there's information about all the software that's available on the instructional systems at this web address, inst.eeks.berkeley.edu/software, and we have a news group that's set up for the entire class, ucb.class.ee140 on news.berkeley.edu. You can post messages either by using a standard news reader or by sending mail to the address right here. From off campus, if you want to access the news group, you can do it through Google or through this other website. And as I mentioned before, this section and all the lectures are webcast off of webcast.berkeley.edu. HSpice is the circuit simulator that you're going to be using in the class. You should have your paths set up such that when you type which HSpice at the command prompt from your instructional account, this path should show up. Similarly with A-Waves, if you don't have that, send mail either to the TAs if you don't know how to set up your paths appropriately, or maybe to, I guess, the instructional computing help desk. We have, well, anyways, you can just read through the rest of this stuff about running HSpice. Documentation for the for the tools, HSpice and A-Waves is in this path. There's a path off that called PDF, which has PDFs of all the manual documentation. You might want to refer to some of that information at some point later on over the course. And there's also documentation at the web address. So the examples down here are some HSpice HSpice files that you could run in HSpice to generate output, and we'll go through that at the end of the class. So any questions about the administrative stuff? Okay. So the general outline, can we zoom out on the overhead? Great. The general outline for today's class, for today's discussion, is basically going to be going over some of the lecture material that Professor Broderson has presented over the course of the week. And what I thought we'd talk about were some outline, some MOS large signal equations, understanding the various large signal equations and the various modes of operation that a transistor can be in. There's that. From there, deriving and understanding the small signal parameters. For instance, we have these equations that calculate, the IDS of a transistor based on the various DC biases applied to the transistor. And we also have these equations that you can use to calculate what GM or R out of the transistor is. And it's important to understand that these sets of equations are self-consistent, that basically the small signal model is derived explicitly from the large signal model. Okay? And so we'll go through some of that, and then sort of showing a low frequency small signal model of an MOS transistor, and then finally some review of HSpice if there's time. So that's basically what we're going to be talking about today. If at any time anyone has any question, by all means, feel free to interrupt me. I'm going to probably, if it's an important question that we want to share with the rest of the class, I'm going to ask you to say it into the microphone so that the people listening through webcasting can hear it as well. Okay. So moving along. So the large signal model for an MOS, and I'm assuming a level 1 model, which is also known as the simple square law model. Now that's going to be the model that we start with for the MOS transistor. In reality, as you'll learn as you get more experience with working with transistors in the analog domain, the level 1 model really isn't all that valid with modern processes. As feature sizes have shrunk, a lot of second order effects have come in that modify really what the large signal equations look like, and hence limit the usefulness of the level 1 model. But for right now, and for all intents and purposes, we're going to assume that the level 1 model is valid. We're going to, later on over the course of the semester, look at some of the changes that need to be made to the level 1 model in order to account for non-idealities and second order effects in current MOS transistors. But by and large, just a data point in MOS history, the large signal model is pretty valid for device lengths in transistors longer than around 3 or 4 microns. Current transistor technology is working at around 0.13 microns device length, and 90 nanometer is coming out shortly. Those devices are not quite ready for full commercial manufacturing, but so you're kind of, I guess, a factor of around 30 smaller than the device length, where level 1 model is really valid. But for a first pass, it's good enough to use. So we've got, I'm going to be using an NMOS transistor just to keep things straightforward, but the equations for PMOS are identical. So you've got your gate, your source, your drain, and your bulk node. Okay? And IDS flows in that direction, from drain to source, okay, for an NMOS. And the important thing about an NMOS transistor is that actually in fabrication, the drain and the source are symmetrical, and the only difference between understanding which terminal is the drain and which is the source is basically which of these two terminals has a higher potential. So by definition, VD is greater than or equal to VS. Okay? So as Professor Broderson discussed, I think on Monday, there are 3 modes of operation for this transistor. Oops, thank you. VD is greater than or equal to VS. Right? So the first one is cutoff. And cutoff basically means no current is flowing. And cutoff exists when VGS is less than or equal to VT. Okay? Or conversely, VGS minus VT is less than or equal to 0. Okay? Now, just a quick notational point is that whenever VGS basically means VG minus VS, right? Whenever you have two nodes listed as a subscript to a voltage or a current, it means, for a voltage, it means the difference between the first node and the second node. For a current, it means current flow from the first node to the second node. So IDS is the current flowing from the drain node to the source node. Okay? And this VGS minus VT is a parameter that's going to come up a lot. It's called a lot of different things. It's called VDSat. It's called V overdrive. I will sometimes call it VGT, as VGS minus VT. All of these terms are interchangeable. The point being, in cutoff, no current flows. So if VGS minus VT is less than or equal to 0, IDS equals 0. Basically, this transistor looks like an open circuit. There isn't enough voltage potential across the channel to actually invert the channel. So it's the channel from drain to source looks like high impedance and no current flows. Okay? It's pretty uninteresting in that mode. It's off. It's as if it's not there. Second mode is linear. Okay? And that occurs when VGT is greater than 0, but VDS is less than VDSat, which is VGT. These are the same thing. Okay? So in this case, the current has a form of K prime W over L. Yes.
Question. Did you say VGT greater than 0? Isn't it supposed to be VGS?
Okay. What is VGT? VGT is VGS minus VT.
Yeah, but it's also VGS minus VT. You also said it is equal to VDSat, right?
Right. So, okay. Let me take a step back. In order for the linear case, in order for the transistor to be in linear mode, the channel needs to be inverted. There needs to be negative charges in the channel so that the N plus region here and the N plus region here have a conducting path. In order for that to happen, VGS needs to be greater than VT, which means that VGS minus VT has to be greater than 0. My shorthand here is VGT. Okay? So this is equivalent to saying VGS is greater than VT. So that's condition 1 for linear. Condition 2 for linear is that VDS is not bigger than VDSat. Okay? And implicitly, VDS is always greater than or equal to 0 because by definition, VD is greater than VS. Okay? So the current equation looks like this. VGT minus VDS over 2 times VDS times 1 plus lambda VDS. Okay? So I'll box that so you can see it. And let's, for the time being, ignore this. And a question for you. Can anyone guess as to why this mode is called the linear mode? Is there any, does anyone have any intuition as to why this mode of operation is referred to as linear? Yeah. Go ahead. Either one of you. You raise your hand. Can you use the microphone?
On the IVDS chart, it looks like it's linear coming from 0, coming from the origin.
Exactly. Exactly. So basically, we know that VGT is bigger than VDS. So VGT is also obviously bigger than VDS over 2. So if VGT happens to be much, much bigger than VDS over 2, then IDS basically it looks like K prime W over L VGT times VDS. So it looks like, the transistor now looks like a linear resistor. You have drain here, you've got source here, and the current is directly proportional to VDS. What does that mean? That means it's a linear device and it actually looks like a resistor, where R equivalent is equal to 1 over this quantity. So it's 1 over K prime W over L VGT. So near the origin with small VDS, exactly what the student said, IDS versus VDS is a straight line. Now we know from our device curves that later on this thing flattens out as the device goes into saturation, but for the time being, this is linear. That's why it's called linear. Okay? Sure. Can you use the microphone?
Channel length modulation is a result of pinch-off, right? Why would we include it at all then in a triode region equation?
Very good question. So the question was, why are we including this term in the linear region when this channel length modulation is an effect of pinch-off, which only sets in the saturation mode? And the reason is really kind of boring in that it's to make the curves fit. In that as VDS goes to VDSat in saturation mode, this term goes to the 1/2 K prime omega W over L VGS minus VT. And so in order not to have a current discontinuity in the saturation mode, you include this as well. So it's basically, let me go to a next page. So this is VDS, IDS, and VDSat. Here, you do that, and if lambda is 0, the two curves, the two IDS definitions, meet exactly here. But if lambda is non-zero and it's not modeled in this region and is modeled in this region, you'll have that, and you'll have a current discontinuity. So realistically what they do is they just do some model extraction curve fitting. They include lambda here with lambda, without lambda here, oops, this guy, so that there's current continuity. You basically, in all your models, you want continuity to the 0th order. You also want continuity to the 1st order. If you can make your models differentiable to more degrees, to higher order, then generally your models are going to be more accurate because things that are physical don't really display true discontinuities. Okay? It's a real good question, though. All right, so let me move that aside. Any other questions on linear mode? Okay. And then finally, page 3, saturation. The conditions here are VGT greater than 0 and VDS greater than VDSat, which is VGT. And in this case, basically pinch off occurs. So to first order, the current is no longer dependent on VDS, which is why it's called saturation. The current saturates at a final level. And the equation for this, IDS, is equal to K prime over 2, W over L, VGT squared times 1 plus lambda VDS. So just to draw what the current looks like in the various modes, this is a shape of curve that your guys should all be very familiar with. VDS VDSat. And so if this is lambda equals 0, the current totally flatlines. But realistically, whoops, lambda greater than 0. So as VDS changes, the current of this device also changes. Okay. And as Bob mentioned in lecture, this lambda parameter is important. It's basically, if you have your device here, when it's in saturation, it's a measure of the output resistance. So VG is fixed, it's tied to some battery, and you're sweeping VD, okay? As VD increases, if lambda is 0, that means that no additional current flows through the transistor, which means that if lambda is 0, that transistor is basically just a current source that's a function only of VGS. Okay? In reality, however, as VD increases, or VDS increases, the current IDS also increases. That basically looks like some finite output resistance. So you can start modeling it as something like this, where lambda unequals 0. Okay? Is that clear to everyone? Okay. Any questions about that? Okay. Now, just take it on face now. It's not intuitively obvious yet from anything you've seen in class that saturation mode is the most important mode of operation for your transistors. Bob alluded to this in lecture, I think on Wednesday, where basically when you do your solution, you assume everything's in saturation, you make all your calculations based on things being in saturation, and then you hope that everything actually is in saturation so that your assumptions are correct. For most active circuitry, we're using the transistor in the saturation mode. As we get to other circuits, where we start putting these devices together, the rationale behind that will be more clear, but just on a real simple basis, the reason why is that with this model over here, where IDS if you assume that lambda is 0, so you have infinite output impedance, IDS is only a function of VGT. So you can sort of see how you've decoupled input and output. And by twiddling the input, you can do some interesting things on the output. And basically those interesting things are things like gain, things like filtering, all sorts of implications that you can't do with the devices in the other mode. So just take it on faith for the time being, and we'll get to it later. Okay, so those are the primary large signal equations that you guys need to be familiar with and know and be comfortable with moving forward in the class. And as long as you're on top of these large signal equations, then you'll be able to pick up most of the other stuff that goes on. One bit of added trickery that I forgot to mention is that we always assume, VGT is VGS minus VT. And we always kind of assume that VT is constant, that you're only really controlling VGS. And as we know from the back body effect, that's not true. And so, just one more note, VT is not necessarily constant. And the equation for VT is a function of VSB, and it's your VT0, which is your constant VT, plus gamma times okay, so this is your equation. VT is some constant that's given. Gamma is another constant. And this 2 phi f is related to the band structure of silicon, and is basically 600 millivolts or thereabouts. So VT is a function only of VSB, and just to remind you, drain, gate, source, bulk. So what VSB is this voltage, right? It's the voltage between the source and the bulk, okay? With an NMOS transistor, let me draw it here. So this is your gate node, this is your source node, and this is an N+. N+, this is your drain node, and this is your bulk, which is a P region. The source can be a higher voltage than the bulk, so VSB can be positive without impact. This NP diode, which looks like that, when VSB is greater than 0, will be negatively biased, so very little current will be reverse biased, so very little current will flow here. Small current. However, in an NMOS transistor, if the bulk voltage is raised significantly higher than the source, then you start turning this diode on. And this, Bob mentioned this in class, a student mentioned this in class, I think on Wednesday, and then you've got a lot of current. Once VBS is greater than, say, around 0.6, this diode turns on full blast and sources a lot of current, and the basic action of your transistor is all fouled up. So by and large, with an NMOS transistor, you want to guarantee that that never happens. So the bulk node is typically tied to your lowest potential. Let me box this off. So typically what happens is that your bulk node is tied to your ground. Your bulk node is tied to ground with an NMOS, and your bulk node is tied to VDD with your PMOS. Okay? And just a word of caution about the VT equations is that both in Gray and Meyer and I believe the Razavi textbook, they hop around between VSB and VBS all the time. depending on what they're trying to prove. So just keep in mind that VSB is equal to the negative VBS, so that you don't get confused and your equations don't get fouled up. Okay? Any questions on this? Okay. So something to keep in mind is that by changing VSB, you're changing VT. And by changing VT in saturation, you're changing VGS minus VT, which means that your current changes. So in saturation, your body voltage does have a direct effect, although a bit convoluted, on what your output current is. Okay? So it's really not, so IDS here is not completely a function, or not necessarily completely a function of VGS minus VT. It might also be a function of your bulk voltage. All right. So moving on to the next topic. What page was that? That was page 4. So this is page 5. Small signal parameters. So without going into too much gory mathematical detail, these small signal parameters are, things like GM and R out, which hopefully you guys have heard of before, aren't mystical quantities that are calculated out of nothing, but they're based directly on your large signal equations. And what we're trying to do here is you've got, VDS, IDS. What we're doing here is taking the slope, of your current and voltage curves at particular points in order to calculate these small signal parameters. And what I mean by that, did someone have a question? Okay. What I mean by that is, let's say you want to know what let's say your operating point is right here. Okay? Your operating point is right there. And you want to know what a small change in VDS does to your current, right? And obviously what you care about is the partial derivative of your current with respect to VDS at that operating point. And then in order to get delta I, you multiply that by delta VDS. Right? We're linearizing our circuit at a specific operating point to find out what small changes do to the overall behavior of the transistor. Okay, and that can basically be expressed. We have y is some output function y is some output variable y is some function of x, which can be expressed as f of x naught plus delta x, where this is some known operating point. And as hopefully all of you know, you can do a Taylor expansion of this and get f of x naught, which is basically the DC operating point at which you're operating, plus df dx at x naught times delta x plus higher order terms. Okay? So this can be directly related to to your these functions f, y, and x can be directly related to the quantities we care about, which are VDS, VGS, and IDS. So here, the analogy to transistors is IDS is basically a function of VGS, VDS, VBS. Okay. And that can be expanded. And then if we wanted plus, delta VGS plus delta VBS, DS, and so on, that can be expanded to function of VGS, VDS. I'm going to ignore VBS just to keep things simple. Plus dF dVGS evaluated at VGS VDS times del VGS plus the partial derivative with respect to VDS times delta VDS. Okay? So, does everyone understand sort of the mathematical steps that I'm taking here? I'm just doing a partial expansion. And I'm using the notation f just to indicate the function of what ID is as of VGS and VDS. So what we really care about here is, so f is really IDS as a function of these variables. Okay? And therefore, what we're defining as GM, we're defining as DF dVGS, which is equivalently DID dVGS. Okay? And similarly, 1 over R out is equal to, is defined as dF dVDS. Okay? So I want to leave, can you scroll up a bit so we just have the last bit? Okay. So when you plug all this stuff together, you have IDS, which is the total current, is equal to IDS, this is your DC operating point, plus GM times delta VGS plus 1 over R out times delta VDS. Okay? And so at this point, I want to pause real quick to talk about some notation that's used in just about every textbook. Because we have IDS on the left side, IDS on the right side as well. But this is lowercase ds, and this is uppercase ds. Okay, so the notation in the book, when you have voltages or currents where the I and V are capitalized as are the nodes that you're referring to, that's the DC operating point, okay? So that's basically the fixed point about which you are evaluating your derivatives and so forth. When you have lowercase I and lowercase nodes, that refers to the small signal quantity. In other words, the tweak from the small change that's superimposed on top of the DC operating point. And when you have a capital letter for your I and V and a lowercase for your subscript, that's basically the DC plus the small signal superimposed upon it. So for instance, VGS is equal to VGS plus VGS. And yeah, that's a little aggravating because you're summing up a bunch of VGSs and getting a VGS, but this is a notation that's common convention, so it's important that that you understand that, or at least recognize it when you get to when you're reading the textbooks. Okay, so now what we know here is that the definition of GM is the partial derivative of ID with respect to VGS. So given that, and given our knowledge of small signal equations, or excuse me, of large signal equations, we can formally derive what GM actually is. So in saturation, which I mentioned before, is the mode we really care about, IDS is equal to K prime over 2 W over L VGS minus VT squared times 1 plus lambda VDS. Okay? So GM is defined as dIDS over dVGS. So evaluating the integral, you get 2 times K prime over 2 times W over L VGS minus VT. That's 1 plus lambda VDS. Okay? And again, to keep things simple, let's ignore this. Let's ignore the lambda term. Just basically assume that lambda equals 0. So GM is equal to K prime W over L VGS minus VT. Okay? And from there, you can do all sorts of algebraic manipulations, and I'll show you one to get GM in terms of other quantities. Here you have it in terms of your device size and your VGT voltage. But as you will find, and again, take this on faith for the time being, it's typically much nicer to deal with your small signal parameters in terms of bias current. So let's see what we can do, what algebraic manipulations we can do to express GM in terms of bias current. Okay? So let's square both sides. So we get GM squared is equal to K prime W over L times K prime W over L times VGS minus VT squared. Okay? And I'm going to put a 1/2 here and a 2 there. Doing everything fair so far. And we notice, oh hey, this term is IDS. So we get GM squared is equal to 2K prime W over L times IDS, which implies that GM is equal to the square root of 2K prime W over L times IDS. So two different forms for GM in terms of IDS or in terms of VGT. So there are three basic parameters here: IDS, W over L, and VGS minus VT. And you can express GM in terms of any two of those three. So you do more algebraic manipulations, and you also get that GM is equal to 2ID over VGS minus VT. And in different scenarios, the exact expression you want to use will differ depending on what you're trying, what design parameters you have a choice of selecting. But all three of these equations are totally equivalent and self-consistent. There's no mystery here. So I would like to persuade you guys to understand how these different forms of GM are related. You might want to try deriving this just to understand how we got there. Okay? It's not very tricky. It's just a couple of lines of algebra. All right? So because we're a little short on time, I was going to go through the derivation of GMB, which is the back body, basically the back body transconductance. As I mentioned before, changing the bulk voltage changes the threshold voltage, and changing the threshold voltage changes the overall device current. Therefore, you can expect that just like there's a small signal parameter that expresses a change in VGS as a change in current, there's a small signal parameter that expresses a change in VBS into a change in current. Yeah, we're a little short on time, so I don't want to go through that math. It's all in both the Razavi and the Gray and Meyer textbook, so you can look through it yourself. But the warning there is, as I mentioned before, they keep swapping around between VBS and VSB, and it's very important that you not get confused and you keep track of sign, because otherwise things will get fouled up again. Okay, and you can do the same. You can do the same thing with R out, and basically what you get for R out is equal to 1 over lambda ID. Same type of mathematics. So you might want to do that as well, just to basically convince yourself that these small signal parameters are not made out of thin air. Okay? So what that leaves us is a pictorial representation of our small signal model. So our transistor has 4 terminals, a gate, a drain, a source, and a bulk. Are there any questions before I continue? Is everyone sort of understanding the general concepts that I'm going over? Okay. If at any point any of you guys think I'm going too fast, please tell me. You don't have to tell me here. You can send me email. You can stop by office hours. But if I lose you guys and no one tells me that I'm going too fast, I'll basically continue at that pace. So yeah, just give me feedback. I haven't taught this class before. I've taught other classes. So please, stop me if I start either confusing you or going too quick or whatever. So anyways, with that little disclaimer aside, we can transform this into our small signal model. So we've got our gate node, plus minus, VGS. And now you'll note I'm using I'll show you in just a second. You'll note that in all my terms, I use the lowercase because we're talking about small signal. Lowercase v, lowercase gs. Okay? So if you're actually to sort of draw a small signal schematic of this transistor in saturation with the parameters that we've derived so far, you've got VGS here. The current that's derived from this small signal VGS flows from drain to source, and it's the transconductance times VGS. Similarly, the back body transconductance that I mentioned before, a change in VBS also results in a change of current from drain to source. So that's here. Okay? Similarly, a change in the drain source voltage also results in a change in the drain source current. And because it's a linear relationship, we could draw this as 1 over R0 times VDS, but basically a dependent current source and a resistor have the exact same behavior. So we typically draw it as a resistor. So this is your low frequency small signal model. As we learn about some other effects, some of the parasitic effects, additional devices will be added into the small signal model. But for the time being, this is the small signal model that you work with. Okay, does everyone understand how we got the basic progression of today's section was large signal model, small signal parameters, small signal model. Okay, so that's the basic point that I wanted to get across. Does anyone have any questions about that sort of conceptual progression? Yeah. That's a really good question. So the question, because I'll repeat it, was, okay, you've got this small signal stuff. Why don't we care about the large signal currents that are flowing in there as well. And the reason is really it's application driven. What will typically happen is that these transistors, you might have just to keep it real simple. So you apply some DC bias and you've got some small signal VGS. And so you've got IDS plus IDS. And so you've got V out plus V out. So why don't we care about this term, and this term in our small signal analysis? And it's really from an application standpoint. It's because like this transistor configuration is actually being used as an amplifier. It's a common source amplifier, and hopefully you guys have seen it before. The signal that we're actually amplifying is this. And the stuff that we actually care about at the output is this. This V out is known. It's just sort of a voltage that's sitting there. So we really don't care about it. So because of that, we basically ignore it in the small signal model. And it's also because the small signal model is only valid because we're linearizing around an operating point, around a known operating point. So we're linearizing around the operating point of IDS, capital VO, and this capital VGS. So the parameters, another way of answering your question, is that the parameters GM, GMB, and R out those parameters are wholly based on your large signal quantities. Okay? That's a good question. It looks like we're just about out of time. I didn't have time to go over some of these HSpice netlist files in the handout, but I'll stick around here for a couple minutes. If anyone is really confused about HSpice, I can answer some questions, and you can send me email as well. A reminder, put EE140 in the subject of any email you send me because it'll get it read quicker. Okay? And if you have any feedback about this section as well, also please let me know. Okay.
There's a 12:30 class.
Okay. All right. I'll anyone who wants to stick around, who needs a quick review of HSpice, stick around. Find a partner who has one of these sheets if you don't have it, because that's what you need to know.
Can I ask you a non-HSpice?
Yes. And so all of the people who are here for HSpice, and that's it. Just go sit down, and then we'll get to it in just a minute.
Okay. I was looking at the homework.
Yep.
And I was doing part B,
Yep.
finding, let's say I wanted to find GM.
Okay.
I guess one way of doing it is just going right to the operating point of A
Uh-huh.
and using the equation to IDS over VGS minus VT.
Sure.
I know IDS, VGS, VT, so
Yep.
just plug and chug.
Yep.
What if I use the derivative property of GM being the small displacement of IDS over a small displacement of VGS?
The issue there is that you don't have a small displacement of VGS to deal with. You have a 300 millivolt displacement of VGS.
Uh-huh.
You don't have a small one.
That's not, yeah, that's
It's not really. It's not really small enough. I mean, you could use that as an approximation and compare it.
Yeah, and I got similar answers. But,
So there you go.
okay, except when I did the approximation type deal with RO, and I got pretty different answers. I got like 3 kilo ohms versus 4 kilo ohms. So I should.
Okay. Here's one other comment about homework 1 is that these curves are based on actual device measurements in the lab of 0.13 micron.
It's not theoretical, right?
These are not theoretical. So as I mentioned before, like real devices don't behave according to level 1.
Okay.
There are other effects going on.
Okay.
So depending on how you calculate VT, I went through this exercise myself. The other TA made this homework.
Uh-huh.
You can get a VT that varies by a couple hundred millivolts.
Okay.
It's because the model's not valid. So don't worry about, for this one, don't worry about 20 to 30% discrepancies. Just make sure that you're confident in your mathematical technique to get those numbers.
Okay.
And you can even say, look, this stuff varies based on different techniques.
So the derivative property wouldn't be a good thing.
No, derivative property for RI would be great because you've got basically like 50 millivolt increments, right?
Right. Yeah, that's what I use. I use a really small increment.
Yeah, so that's fine.
Okay.
That's fine.
Okay.
And you can sort of see that R out, that V, excuse me, that I isn't changing very much for R out, right? So therefore, that's the definition of small. Like you're not seeing some wild curvature in these curves, so the slope is basically constant here.
Okay.
And so,
Right.
okay?
Sounds good. Thank you.
Yeah, no problem. Yes?
Even you said that R0 is equivalent to a dependent current source.
Uh-huh.
So is that GM times VDS?
No, not GM times VDS. It's GDS.
GDS?
What GDS is the inverse of 1 over R0. Here, let me do that real quick on the board, assuming there's chalk. So you're familiar with the notion of conductance. Conductance is 1 over resistance, right? Let's assume Gx times Vx. Okay? You do this. This is the exact same, and you'll have to convince yourself of this fact. Is that step obvious? Because what's the current of this is Vx. Vx equals I times R. So Vx equals I over Gx. Okay? What's this? I equals Gx times Vx. You know, so which means that Vx equals I over Gx. Same thing. So you can call a resistor is a voltage-controlled current source. It's just that the controlling voltage and the thing that controls it are its actual terminals. So because of that, you can just sort of call it a resistance. And that's the convention because people like thinking of physical devices as opposed to, this is a theoretical device, a resistance is real, it's physical. Okay? All right, so you guys are all here for an HSpice, the HSpice stuff, right? No other questions? Okay, so look at the examples at the bottom of the slide. Excuse me, at the bottom of the handout. And if you don't have a handout, look on with someone else. And I'll just sort of go over the basic form of what HSpice netlists look like. So let's look at example 1, which starts with dot title. Okay, does everyone have the handout in front of them? So dot title is exactly what it implies. It's the title of the file. Not very interesting. The next statement, dot options. Dot options is a statement that says, these are the options for simulation that I want to run. The important thing to use is dot option post, but by and large, just copy what we have here. Okay?
What does the dot mean?
What do they mean? Good question. I don't remember all of them. Dot post means print the output to a post file that can be interpreted by A waves to give you a graphical output. I think dot list prints your outputs to a text file, and I don't recall what dot node does. Here's something, the thing to keep in mind, actually, is that above it where it says demo and tutorial files are under blah, 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 if you go to that document and then go to that directory and then go to the subdirectory PDF, you have all the HSpice documentation you need. Okay, so that's one place to look, to just sort of poke around, either refamiliarize yourself with HSpice. How many of you have never used either HSpice or PSpice before? Okay, so everyone else just wants to familiarize it. You'll probably want to spend a bit more time, and because you need to. This is a very important tool. You will need to understand how to use it in order to pass this course. A lot of the homeworks and all of the design projects use this. So real briefly, what HSpice is a circuit simulator. You describe a netlist, and you describe what modes of analysis you want to run on that netlist, and it generates the output for you. Okay, so what does .op mean? What that means is print the operating point. So based on the netlist that's going to be described, it just gives you the DC solution. Okay? Then the next statement, .ac dec 10 to 1k 1 meg. Okay. Parse it. Again, all this stuff is actually in the documentation. So I suggest if this is absolutely Greek to you, or you want to know some of the other options that you can do, because I don't remember all of them. I refer to the documentation all the time. You should as well. .ac means do an AC analysis, which is a small signal analysis. DEC means sweep the frequency. So that means you're going to, with the .ac, you're typically going to sweep frequency. DEC means sweep the frequency logarithmically by decade. This means 10 points per decade. So it calculates 10 frequencies per decade. So between this is the start frequency, f start. This is f stop. So what this analysis does is it calculates a small signal frequency response at between 1 kilohertz and 1 megahertz, 10 points per decade. So there are 3 decades here, right? 3 orders of magnitude. So it'll calculate 30 points. And it might be 31 because of the endpoints. But it'll be like, and it'll do it in a logarithmic fashion. So it'll calculate 10 points between 1K and 10K, 10 points between 10K and 100K, and so on and so forth. Okay? The next line, .print AC V1, V2, ... What this says is print out the results of my AC analysis. .print AC, and it says the voltage of node 1, voltage of node 2, and then the current through R2 and the current through C1. Okay? So the way this is defined, it's kind of putting the cart before the horse. It's telling you what you're doing to the netlist with the netlist before actually understanding the netlist. And the important part of HSpice is the netlist itself, the description of the circuit in your file. So that's in the next stuff, the next few lines. And any device, so each of these is instantiating a device. So any device that starts with a V corresponds to a voltage source. Anything that starts with an R corresponds to a resistor. Anything that corresponds to a C is a capacitor. So it's defined, and if this stuff is total Greek to you, you'll probably have to read the documentation more because it kind of makes sense to me, so I just explain it the best I can. So this V1, 1, 0, DC equals 10, AC equals 1. It's saying instantiate a voltage source between nodes 1 and 0. So we've got 0, node 0, which always has to exist in your circuit. That is global ground. And you've got this voltage source, which we're calling V1, that's connected between node 0 and this node, which is node 1. It has a DC voltage of 10 volts and an AC magnitude of 1 volt. Okay? So in DC analysis, this is a 10-volt battery. In AC analysis, it has a twiddle, has a small signal superimposed on top of it that has an amplitude of 1 volt. Okay? The next statement says, between nodes, I'm not going to write it out, instantiate a resistance between nodes 1 and 2. This is R1 with a resistance of 1 kilo ohm. Okay? Similarly, R2 is equal to 1 kilo ohm. Okay? And then finally, C1 is connected also between nodes 2 and 0, and it's 1 nanofarad. Okay? So this is what you use to describe your networks. And documentation on the parameters that you can set up for various voltage sources. If you wanted this to be like a square wave for transient analysis, if you wanted this resistance to be nonlinear, you can do all that stuff. It's in the documentation. Look it up. Okay. So now now that we understand the netlist, what we're doing is we're doing an AC sweep of this guy. Excuse me, an AC sweep of this netlist over 1K to 1 meg. And we're analyzing, we're outputting the voltage at node 1, the voltage at node 2, the current through R1, right, that's IR1, and the current through C1.
What does the AC output print?
That means print the results from the AC analysis. Because you could also have, you could do a DC analysis. There are lots of different analyses you can run. One is AC, that's a small signal analysis. One is DC, where basically you're calculating the operating point for a bunch of different DC voltages. And how that differs from the AC is that you can sort of see here. For any DC solution, there's no notion of frequency, so capacitors look like open circuits, right?
So if I don't put AC here, it won't activate that.
It's the safest thing to do. It doesn't, I don't know exactly how the HSpice compiler or netlister or whatever interprets this statement, but if you wanted to look at AC results, then you're best served by putting AC. If you don't put AC, it might spit out an error, it might work fine, it might give you garbage results. Don't know. Yeah?
Can I put DC instead of AC if I want to print out the DC?
Yes. So in addition, you can do multiple analyses in one netlist. You could, in addition to this .AC statement, you could have a .DC statement. Okay? And with a .DC statement, you can sweep all sorts of different things. You could sweep this voltage. If you wanted to, you could sweep this capacitor value, although that would do nothing. More realistically, you could sweep this resistor value. You can do all sorts of stuff. Again, look at the documentation. By and large, for DC analyses, you'll be sweeping DC input voltages. Okay? It's in that directory that I mentioned before on the handout. Do you have a handout? Where it says demo and tutorial files are under share int sww package HSpice 2004.03. Then inside that, there's a PDF subfolder. And inside there are lots of PDF manuals. And it'll take you some searching around to figure out which one is the relevant one. You might also just want to buy the HSpice manuals from a bookstore. I don't know if Ned's or ASCC Bookstore carries it, but I'm sure that you could buy them off of Amazon if you wanted to.
What are the difference between eSpice and
HSpice is a commercial tool. PSpice really, it's the same basic engine. There's some compatibility differences. PSpice, the one that you have access to, runs on the PC and is a student version. For the purposes of this class, all design projects have to be done on HSpice, period, the end. So you might as well just get used to using HSpice. You know, you guys, you have access to the instructional computing. You can do it remotely. So PSpice is just basically the same thing, but we're not letting you use it. Yeah?
So when you print out the like V1 and V2, which one is it?
I'm sorry?
When you print out like, the print AC V1, V2.
Uh-huh.
So what's the V1 and what's the V2?
Okay, it's the voltage at node 1.
Oh, voltage at node 1.
Yeah. This means voltage at node 1. If instead we called this node foo, to print out the voltage, you'd say voltage foo. Okay?
We don't have to use numerical.
I don't think so. I'm pretty sure you don't.
We can use alpha.
I'm pretty sure you can use alphanumeric. The important thing to remember is that node 0 is reserved. That is ground. Another thing to remember is that HSpice gets confused easily, so don't have nodes that have the same name as devices. Like I wouldn't call a node V1 here, or R1 or C1, because it could get confused. Also, remember that the devices are understood by the first letter. So if you want a voltage source, it has to be V something. It can be V whatever you want, has to be V something. Yeah?
Is it kind of a convention to have your nodes just be numbers?
A lot of the time. You'll find that as you start doing more complicated designs, you won't want to do that. Because if you have a 10-node circuit and they're like, node 9 is operating weirdly. What the hell is node 9? I mean, it's much nicer to call it like output, or input positive, input negative, or VDD or ground or whatever. It's much easier to do that. Yeah?
Does case make a difference, for example, V1?
I don't know. Any other questions so far? Yeah?
For the netlist files, do we have to save it with the extension .sp?
It's good practice. Do it. Yeah, do it. And then to actually run it, I believe what you type at the command prompt. So in order to run this, I believe what you do, and you'll want to double check this. So you'd write HSpice.
So this is right after we log into
This is after you've created your network.
Yeah, of course.
Yeah. This is at the command prompt.
So I created this.
Yeah.
You said the extension is what?
So let's call this, and this is actually a file that you can get off of the web page. I think it's called demo1. Okay. Okay. And again, look at the web page because there's a how-to subpage off the web page, and it goes through all this, or it goes through at least how to run HSpice. So you'd run HSpice.-i. -i means the next thing is your input file. So you'd say demo1.sp. And then just to be safe, you do -o demo1. And what the -o means is create all my output files with this file header. So this will create stuff like demo1.list, demo1.ac0, and a bunch of other output files. The exact extensions of these files aren't important, and it depends on what analysis you run. But basically, by doing -o demo1, that guarantees that, that all the related files have that name. And I think it does it by default anyways, but again, good practice.
What we say what is which HSpice? What does that do?
Okay, that's a unit. Which is a Unix command that tells you, like which HSpice will tell you the path to HSpice that will be run when you run HSpice on Unix. And if you were to type which and then just bang on the keyboard, it would tell you, sorry, that text string is not an executable argument as far as I know. Okay?
So do we have to get into the shared region HSpice
No.
to run it?
No. You should just be able to write, you should be able to do this.
Okay.
First, just to check, you type which HSpice, and you should get the response should be like share bin blah 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 blah.
Which
Okay.
means I have HSpice.
Which means that your paths are set up so that it executes the correct HSpice. It's all a path setting thing. Okay? All right, so that's the simple one. Let's now quickly look at not so simple one, and I have 5 minutes before I have to leave. So, dot title is a dot title. Dot option is, again, options. I don't know what dot no mod means. I just don't recall. Look it up. Then you have a dot model statement. And the dot model is a way to describe more complicated devices. And HSpice knows what an NMOS transistor is. So, so by instantiating dot model, you're saying, I have this circuit that I'm going to call XTOR. XTOR is a device that is an NMOS, and it's described by the following parameters. It's described by a level 1 model with the parameters listed as you see there. And all of those parameters, with the exception of cap op, should be familiar to you. It's VT0, gamma, which is from the VT calculation, lambda, which you know, and K prime, which you know. Cap op, don't worry about. Okay, so then after that is your netlist. And so the first device is M1. So I'll write this out. M tells you MOS transistor. Drain, gate, 0, 0. So the first node is the drain node. Second node is the gate node. Third node is the source. Fourth node is the bulk. So here they don't use numeric convention as when you were asking just a second ago. So what this means is that we've got a transistor connected to ground, The drain node is connected to a node called D. Gate node is connected to a node called G. And we've got a voltage source called VTS, also connected to gate, and a voltage source, hold on, VDS, connected to the drain. So that's the netlist. What's your question?
XTOR is arbitrary.
XTOR is what they named. Yes, XTOR is just what you're choosing to name your model. You could call it my favorite XTOR if you wanted to. Okay?
And can I, in the dot, put the dot, define the U, W, and L in the dot model? Or
I don't think so.
Okay.
I don't think so. Oh yeah, that's the other thing. So the W and L, which are design parameters, and you don't want to do that because W and L, you can have two transistors of different size that are the same model.
Oh.
So W and L are actually part of the device. It's not a model-specific parameter. That's the other thing. And then afterwards are a list of parameters.
So XTOR is like a class, not an actual device.
It's a model.
Okay.
You can call it a class. We call it a model.
Okay.
Okay? Because on a given chip, you can have, this model describes all the devices on the chip, but you can have a big device, you can have a small device. That's a designer parameter. Things like VT0, as circuit designers, we have no control over. As device designers in 130, that's what they control. But this is not a device design class. Okay? And so finally, the last two statements, the dot probe DC. What that tells the compiler to do, or the netlist, or HSpice to do, is it's another way to measure some stuff. Dot probe and dot print are actually the same. I apologize. So they're synonymous. They have the same functionality. So by saying ID equals I1 M1, what this does is it measures I of M1, it meant I1. I don't know what I1 is. It measures the current through M1, and I1 is probably defined for an NMOS device as I drain the source, because there are lots of currents that are flowing in an NMOS device. You know, at high frequency, you can have current flowing from the gate to the source, from the source to the bulk, and all sorts of things. So, so in your output, rather than having this term called I1M1, you'll just have a term called ID. That's drain current. You've also got GM equals LX7 of M1. Don't worry too much about this. This LX7 is an alias that enables you to access the GM of an M1 of an NMOS device. This stuff is in the documentation. It's buried pretty deep. I didn't learn this until my second year of grad school, and I did just fine. And then LX8 is an alias to GDS. And again, GDS is defined as 1 over R0, or R0 is defined as 1 over GDS.
So just memorize this and use it.
No, you refer to the documentation.
Okay.
I mean, I looked at the doc. I didn't remember what LX7 was when I was looking at this yesterday, so I tracked it down in the documentation. It's useful. That's why, and if you're going to be sticking around in analog design and taking 240, it's not a bad idea to invest the $50 in getting a manual set for HSpice. Yeah.
You said LX7 just means GM.
Yep.
Okay.
And it's in the documentation, and there are around 60 different aliases. Okay, so I want to get to this last statement, this DC statement. So this is a nested sweep. So you've got two sweeps here. You've got VDS that starts at 0 to 2.5 in 0.01 steps. And you've got another thing, VGS 1 to 2 in 0.5. And I wrote in shorthand because we're short on time. What this will do is it will set VGS to 1. This is the outer sweep. The first one is the inner sweep. Set VGS to 1 and sweep VDS from 0 to 2.5 in 0.01 millivolt steps. So what you'll get is basically like this curve. Then it'll set VGS to 0. This is VDS, VGS. Oops, IDS. Then it'll set VGS to 1.5 because it'll add 0.5 to it and sweep this. And you'll get that, and then you'll do that. So if you were to plot this stuff out in A waves and plot ID, you would get this family of curves. Nested sweeps are pretty useful. Yeah?
We're using Spice to generate the file, and we use A-Waves to plot that?
To view it, yeah. And the A-Waves interface is pretty straightforward. Okay, so just a note, like by and large, we will provide you the template files, like with the dot probes and the dot DCs and the analysis statements. You guys will be designing the net lists because that's where the design is. All the other stuff is just sort of infrastructure. So we'll typically give it to you. Oh, and the most important statement in any HSpice file, if you want it to work, is .end. If you don't put it in there, it'll just sit. I think it just sits there. It waits for the .end before running. And you'll be like, my God, this thing is taking 2 hours and it's done nothing. These computers are slow. But that's not the case. Okay? All right, I think we have to go. If any of you still have questions, you're welcome to walk with me